In thermodynamics, an adiabatic process is one that occurs without transfer of heat or mass of substances between a thermodynamic system and its surroundings. In an adiabatic process, energy is transferred to the surroundings only as work. The adiabatic process provides a rigorous conceptual basis for the theory used to expound the first law of thermodynamics, and as such it is a key concept in thermodynamics. Some chemical and physical processes occur so rapidly that they may be conveniently described by the term, adiabatic approximation, meaning that there is not enough time for the transfer of energy as heat to take place to or from the system. By way of example, the adiabatic flame temperature is an idealization that uses the adiabatic approximation so as to provide an upper limit calculation of temperatures produced by combustion of a fuel. The adiabatic flame temperature is the temperature that would be achieved by a flame if the process of combustion took place in the absence of heat loss to the surroundings. In meteorology and oceanography, the adiabatic cooling process produces condensation of moisture or salinity and the parcel becomes oversaturated. Therefore, it is necessary to take away the excess. There the process becomes a pseudo-adiabatic process in which the liquid water, salt that condenses is assumed to be removed as soon as it is formed, by idealized instantaneous precipitation. The pseudo-adiabatic process is only defined for expansion, since a parcel that is compressed becomes warmer and remains undersaturated. Description. A process that does not involve the transfer of heat or matter into or out of a system, so that Q equals 0, is called an adiabatic process, and such a system is said to be adiabatically isolated. The assumption that a process is adiabatic is a frequently made simplifying assumption. For example, the compression of a gas within a cylinder of an engine is assumed to occur so rapidly that on the time scale of the compression process, little of the system's energy can be transferred out as heat to the surroundings. Even though the cylinders are not insulated and are quite conductive, that process is idealized to be adiabatic. The same can be said to be true for the expansion process of such a system. The assumption of adiabatic isolation of a system is a useful one, and is often combined with others so as to make the calculation of the system's behavior possible. Such assumptions are idealizations. The behavior of actual machines deviates from these idealizations, but the assumption of such perfect behavior provide a useful first approximation of how the real world works. According to Laplace, when sound travels in a gas, there is no time for heat conduction in the medium and so the propagation of sound is adiabatic. For such an adiabatic process, the modulus of elasticity, Young's modulus, can be expressed as E. Gamma P, where gamma is the ratio of specific heats at constant pressure and at constant volume, gamma Cp, Cv, and P is the pressure of the gas. Various applications of the adiabatic assumption. For a closed system, one may write the first law of thermodynamics as delta U equals Q plus W, where delta U denotes the change of the system's internal energy, Q the quantity of energy added to it as heat, and W the work done on it by its surroundings. If the system has rigid walls such that work cannot be transferred in or out, W equals 0, and the walls of the system are not adiabatic and energy is added in the form of heat, Q greater than 0, and there is no phase change, the temperature of the system will rise. If the system has rigid walls such that pressure-volume work cannot be done, and the system walls are adiabatic, Q equals 0, but energy is added as isochoric work in the form of friction or the stirring of a viscous fluid within the system, W greater than 0, and there is no phase change, the temperature of the system will rise. If the system walls are adiabatic, Q 0, but not rigid, W does not equal 0, and, in a fictive idealized process, energy is added to the system in the form of frictionless, non-viscous pressure-volume work, and there is no phase change, the temperature of the system will rise. Such a process is called an isentropic process and is said to be reversible. Fictively, if the process is reversed, the energy added as work can be recovered entirely as work done by the system. If the system contains a compressible gas and is reduced in volume, the uncertainty of the position of the gas is reduced, and seemingly would reduce the entropy of the system, but the temperature of the system will rise as the process is isentropic, delta S. 0. Should the work be added in such a way that friction or viscous forces are operating within the system, then the process is not isentropic, and if there is no phase change, then the temperature of the system will rise. The process is said to be irreversible, and the work added to the system is not entirely recoverable in the form of work. If the walls of a system are not adiabatic, and energy is transferred in as heat, entropy is transferred into the system with the heat. Such a process is neither adiabatic nor isentropic, having Q greater than 0, and delta S greater than 0 according to the second law of thermodynamics. Naturally occurring adiabatic processes are irreversible, entropy is produced. The transfer of energy as work into an adiabatically isolated system can be imagined as being of two idealized extreme kinds. In one such kind, there is no entropy produced within the system, no friction, viscous dissipation, etc., and the work is only pressure-volume work, denoted by PdV. In nature, this ideal kind occurs only approximately, because it demands an infinitely slow process and no sources of dissipation. The other extreme kind of work is isochoric work, dV equals 0, for which energy is added as work solely through friction or viscous dissipation within the system. A stirrer that transfers energy to a viscous fluid of an adiabatically isolated system with rigid walls, without phase change, will cause a rise in temperature of the fluid, but that work is not recoverable. Isochoric work is irreversible. The second law of thermodynamics observes that a natural process, of transfer of energy as work, always consists at least of isochoric work and often both of these extreme kinds of work. Every natural process, adiabatic or not, is irreversible, with delta S greater than 0, as friction or viscosity are always present to some extent. Adiabatic heating and cooling. The adiabatic compression of a gas causes a rise in temperature of the gas. Adiabatic expansion against pressure, or a spring, causes a drop in temperature. In contrast, free expansion is an isothermal process for an ideal gas. Adiabatic heating occurs when the pressure of a gas is increased from work done on it by its surroundings, e.g., a piston compressing a gas contained within a cylinder and raising the temperature, where in many practical situations heat conduction through walls can be slow compared with the compression time. This finds practical application in diesel engines which rely on the lack of heat dissipation during the compression stroke to elevate the fuel vapor temperature sufficiently to ignite it. Adiabatic heating occurs in the Earth's atmosphere when an air mass descends, for example, in a katabatic wind, föhn wind, or Chinook wind flowing downhill over a mountain range. When a parcel of air descends, the pressure on the parcel increases. Due to this increase in pressure, the parcel's volume decreases and its temperature increases as work is done on the parcel of air, thus increasing its internal energy, which manifests itself by a rise in the temperature of that mass of air. The parcel of air can only slowly dissipate the energy by conduction or radiation heat, and to a first approximation it can be considered adiabatically isolated and the process an adiabatic process. Adiabatic cooling occurs when the pressure on an adiabatically isolated system is decreased, allowing it to expand, thus causing it to do work on its surroundings. When the pressure applied on a parcel of air is reduced, the air in the parcel is allowed to expand. As the volume increases, the temperature falls as its internal energy decreases. Adiabatic cooling occurs in the Earth's atmosphere with orographic lifting and Lee waves, and this can form pileus or lenticular clouds. Adiabatic cooling does not have to involve a fluid. One technique used to reach very low temperatures, thousandths and even millionths of a degree above absolute zero, is via adiabatic demagnetization, where the change in magnetic field on a magnetic material is used to provide adiabatic cooling. Also, the contents of an expanding universe can be described, to first order, as an adiabatically cooling fluid. See heat death of the universe. Rising magma also undergoes adiabatic cooling before eruption, particularly significant in the case of magmas that rise quickly from great depths such as kimberlites. Such temperature changes can be quantified using the ideal gas law, or the hydrostatic equation for atmospheric processes. In practice, no process is truly adiabatic. Many processes rely on a large difference in time scales of the process of interest and the rate of heat dissipation across a system boundary, and thus are approximated by using an adiabatic assumption. There is always some heat loss, as no perfect insulators exist. Ideal gas reversible process. The mathematical equation for an ideal gas undergoing a reversible, i.e., no entropy generation adiabatic process can be represented by the polytropic process equation P V N equals constant display style PV caret N equals text constant, where P is pressure, V is volume, and for this case N equals gamma, where gamma equals C P C V equals F plus 2 F display style gamma equals frac C underscore P C underscore V equals frac F plus 2 F, Cp being the specific heat for constant pressure, Cv being the specific heat for constant volume, gamma is the adiabatic index, and F is the number of degrees of freedom, 3 for monatomic gas, 5 for diatomic gas and collinear molecules, e.g. carbon dioxide. For a monatomic ideal gas, gamma 5/3, and for a diatomic gas such as nitrogen and oxygen, the main components of air, gamma 7/5. Note that the above formula is only applicable to classical ideal gases and not Bose-Einstein or Fermi gases. For reversible adiabatic processes, it is also true that P 1 minus gamma T gamma equals constant display style P caret 1 gamma T caret gamma equals text constant V T F 2 equals constant display style VT caret frac F 2 equals text constant, where T is an absolute temperature. This can also be written as T V gamma minus 1 equals constant display style TV caret gamma minus 1 equals text constant. Topic: Example of adiabatic compression. The compression stroke in a gasoline engine can be used as an example of adiabatic compression. The model assumptions are, the uncompressed volume of the cylinder is 1 liter 1 L. 1000 cc 0.001 m3, the gas within is the air consisting of molecular nitrogen and oxygen only, thus a diatomic gas with 5 degrees of freedom, and so gamma 7/5, the compression ratio of the engine is 10:1, that is, the 1 L volume of uncompressed gas is reduced to 0.1 L by the piston, and the uncompressed gas is at approximately room temperature and pressure, a warm room temperature of approximately 27 degrees Celsius, or 300 K, and a pressure of 1 bar. 100 kilopascals, i.e. typical sea level atmospheric pressure. P 1 V gamma equals constant 1 equals 100 par times 0.001 m 3 7 5 display style p underscore 1 v caret gamma equals operator name constant underscore 1 equals 100 tilde text par times 0.001 tilde text m caret 3 caret frac 7 5 equals 10 5 times 6.31 times 10 minus 5 par m 21 5 equals 6.31 par m 21 5 display style equals 10 caret 5 times 6.31 times 10 caret minus 5 tilde text par text m caret 21 fifths equals 6.31 tilde text par text m caret 21 fifths. So our adiabatic constant for this example is about 6.31 pascals m 4.2. The gas is now compressed to a 0.1 L (0.0001 cubic meters) volume. We will assume this happens quickly enough that no heat can enter or leave the gas through the walls. The adiabatic constant remains the same, but with the resulting pressure unknown. P 2 V gamma equals constant 1 equals 6.31 par m 21 5 equals p times 0.0001 m 3 7 5 display style p underscore 2 v caret gamma equals operator name constant underscore 1 equals 6.31 tilde text par text m caret 21 fifths equals p times 0.0001 tilde text m caret 3 caret frac 7 5. So solving for p2 equals 6.31 par m 21 5 0.0001 m 3 7 5 equals 6.31 par m 21 5 2.5 times 10 minus 6 m 21 5 equals 2.51 times 10 6 par display style p underscore 2 equals frac 6.31 tilde text par text m caret 21 fifths 0.0001 tilde text m caret 3 caret frac 7 5 equals frac 6.31 tilde text par text m caret 21 fifths 2.5 times 10 caret minus 6 tilde text m caret 21 fifths equals 2.51 times 10 caret 6 tilde text par or 25.1 bars. Note that this pressure increase is more than a simple 10:1 compression ratio would indicate. This is because the gas is not only compressed, but the work done to compress the gas also increases its internal energy, which manifests itself by a rise in the gas temperature and an additional rise in pressure above what would result from a simplistic calculation of 10 times the original pressure. We can solve for the temperature of the compressed gas in the engine cylinder as well, using the ideal gas law. PV equals nRT. N is amount of gas in moles and R the gas constant for that gas. Our initial conditions being 100 kilopascals of pressure, 1 L volume, and 300 K of temperature. Our experimental constant near is P V T equals constant 2 equals 10 5 par times 10 minus 3 m 300 K equals 0.333 par m 3 K minus 1. Display style frac PV T equals operator name constant underscore 2 equals frac 10 caret 5 tilde text par times 10 caret minus 3 tilde text m caret 300 tilde text K equals 0.333 tilde text par text m caret 3 text K caret minus 1. We know the compressed gas has V. Topic 0.1 L and P 2.51 times 106 pascals, so we can solve for temperature T equals P V constant 2 equals 2.51 times 10 6 par times 10 minus 4 m 0.333 par m 3 K minus 1 equals 753 K. Display style T equals frac PV operator name constant underscore 2 equals frac 2.51 times 10 caret 6 tilde text par times 10 caret minus 4 tilde text m caret 3 0.333 tilde text par text m caret 3 text K caret minus 1 equals 753 tilde text K. That is a final temperature of 753 K, or 479 degrees Celsius, or 896 degrees Fahrenheit, well above the ignition point of many fuels. This is why a high compression engine requires fuels specially formulated to not self-ignite, which would cause engine knocking when operated under these conditions of temperature and pressure, or that a supercharger with an intercooler to provide a pressure boost but with a lower temperature rise would be advantageous. A diesel engine operates under even more extreme conditions, with compression ratios of 20:1 or more being typical, in order to provide a very high gas temperature, which ensures immediate ignition of the injected fuel. Adiabatic free expansion of a gas. For an adiabatic free expansion of an ideal gas, the gas is contained in an insulated container and then allowed to expand in a vacuum. Because there is no external pressure for the gas to expand against, the work done by or on the system is zero. Since this process does not involve any heat transfer or work, the first law of thermodynamics then implies that the net internal energy change of the system is zero. For an ideal gas, the temperature remains constant because the internal energy only depends on temperature in that case. Since at constant temperature, the entropy is proportional to the volume, the entropy increases in this case, therefore this process is irreversible. Derivation of PV relation for adiabatic heating and cooling. The definition of an adiabatic process is that heat transfer to the system is zero, delta Q equals zero. Then, according to the first law of thermodynamics, 1 d U plus delta W equals delta q equals 0. Display style text 1 q quad do plus delta w equals delta q equals 0, where do is the change in the internal energy of the system and delta w is work done by the system. Any work delta w done must be done at the expense of internal energy U, since no heat delta Q is being supplied from the surroundings. Pressure volume work delta W done by the system is defined as 2 delta W equals P D V. Display style text 2 q quad delta W equals P dV. However, P does not remain constant during an adiabatic process but instead changes along with V. It is desired to know how the values of dP and dV relate to each other as the adiabatic process proceeds. For an ideal gas, the internal energy is given by 3 U equals alpha N R T. Display style text 3 q quad U equals alpha nRT, where alpha is the number of degrees of freedom divided by 2, R is the universal gas constant, and N is the number of moles in the system, a constant. Differentiating equation 3 and use of the ideal gas law PV equals nRT yields 4 D U equals alpha N R D T equals alpha D P V equals alpha P D V plus V D P. Display style text 4 q quad do equals alpha near dt equals alpha d pv equals alpha p dv plus v dp. Equation 4 is often expressed as do. Topic ncv dt because cv alpha r. Now substitute equations 2 and 4 into equation 1 to obtain minus P D V equals alpha P D V plus alpha V D P. Display style P dV equals alpha P dV plus alpha V dP. Factorize minus P dV minus alpha plus 1 P D V equals alpha V D P. Display style alpha plus 1 P dV equals alpha V dP, and divide both sides by PV minus alpha plus 1 D V V equals alpha D P P. Display style alpha plus 1 frac dV V equals alpha frac dP P. After integrating the left and right sides from V0 to V and from P0 to P and changing the sides respectively, lane P P 0 equals minus alpha plus 1 alpha lane V 0. Display style lane left frac P P underscore 0 right equals frac alpha plus 1 alpha lane left frac V underscore 0 right. Exponentiate both sides, substitute alpha plus 1, alpha with gamma, the heat capacity ratio P 0 equals V 0 minus gamma. Display style left frac p underscore 0 right equals left frac v underscore 0 right caret gamma, and eliminate the negative sign to obtain p 0 equals v 0 v gamma. Display style left frac p underscore 0 right equals left frac v underscore 0 v right caret gamma. Therefore, p 0 v 0 gamma equals 1. Display style left frac p underscore 0 right left frac v underscore 0 right caret gamma equals 1, and p 0 v 0 gamma equals p v gamma equals constant. Display style p underscore 0 v underscore 0 caret gamma equals pv caret gamma equals operator name constant. Topic: Derivation of PT relation for adiabatic heating and cooling. Substituting the ideal gas law into the above, we obtain P n R T P gamma equals constant. Display style p left frac nRT p right caret gamma equals operator name constant, which simplifies to p 1 minus gamma T gamma equals constant. Display style p caret 1 gamma T caret gamma equals operator name constant. Topic: Derivation of discrete formula. The change in internal energy of a system, measured from state 1 to state 2, is equal to 1 delta U equals alpha R N T 2 minus alpha R N T 1 equals alpha R N delta T. Display style text 1 q quad delta U equals alpha R N T underscore 2 alpha R N T underscore 1 equals alpha R N delta T. At the same time, the work done by the pressure volume changes as a result from this process is equal to 2 W equals V 1 V 2 P D V. Display style text 2 q quad W equals int underscore V underscore 1 caret V underscore 2 P dV. Since we require the process to be adiabatic, the following equation needs to be true. 3 delta U plus W equals 0. Display style text 3 q quad delta U plus W equals 0. By the previous derivation, 4 P V gamma equals constant equals P 1 v 1 gamma display style text 4 q quad pv caret gamma equals text constant equals p underscore 1 v underscore 1 caret gamma. Rearranging 4 gives p equals p 1 v 1 v gamma display style p equals p underscore 1 left frac v underscore 1 v right caret gamma. Substituting this into 2 gives w equals v 1 v 2 p 1 v 1 v gamma d v display style w equals int underscore v underscore 1 caret v underscore 2 p underscore 1 left frac v underscore 1 v right caret gamma dv. Integrating w equals p 1 v 1 gamma v 2 1 minus gamma minus v 1 1 minus gamma 1 minus gamma. Display style w equals p underscore 1 v underscore 1 caret gamma frac v underscore 2 caret 1 gamma v underscore 1 caret 1 gamma 1 gamma. Substituting gamma equals alpha plus 1 alpha w equals minus alpha p 1 v 1 gamma v 2 1 minus gamma minus v 1 1 minus gamma. Display style w equals alpha p underscore 1 v underscore 1 caret gamma left v underscore 2 caret 1 gamma v underscore 1 caret 1 gamma right. Rearranging w equals minus alpha p 1 v 1 v 2 v 1 1 minus gamma minus 1. Display style w equals alpha p underscore 1 v underscore 1 left frac v underscore 2 v underscore 1 right caret 1 gamma minus 1 right. Using the ideal gas law and assuming a constant molar quantity, as often happens in practical cases, w equals minus alpha n r t 1 v 2 v 1 1 minus gamma minus 1. Display style w equals alpha nrt underscore 1 left frac v underscore 2 v underscore 1 right caret 1 gamma minus 1 right. By the continuous formula p 2 p 1 equals v 2 v 1 minus gamma. Display style frac p underscore 2 p underscore 1 equals left frac v underscore 2 v underscore 1 right caret gamma, or p 2 p 1 minus 1 gamma equals v 2 v 1. Display style left frac p underscore 2 p underscore 1 right caret frac 1 gamma equals frac v underscore 2 v underscore 1. Substituting into the previous expression for w equals minus alpha n r t 1 p 2 p 1 gamma minus 1 gamma minus 1. Display style w equals alpha nrt underscore 1 left frac p underscore 2 p underscore 1 right caret frac gamma minus 1 gamma minus 1 right. Substituting this expression and 1 in 3 gives alpha n r t 2 minus t 1 equals alpha n r t 1 p 2 p 1 gamma minus 1 gamma minus 1. Display style alpha near t underscore 2 t underscore 1 equals alpha nrt underscore 1 left frac p underscore 2 p underscore 1 right caret frac gamma minus 1 gamma minus 1 right. Simplifying t 2 minus t 1 equals t 1 p 2 p 1 gamma minus 1 gamma minus 1. Display style t underscore 2 t underscore 1 equals t underscore 1 left frac p underscore 2 p underscore 1 right caret frac gamma minus 1 gamma minus 1 right. T 2 t 1 minus 1 equals p 2 p 1 gamma minus 1 gamma minus 1. Display style frac t underscore 2 t underscore 1 minus 1 equals left frac p underscore 2 p underscore 1 right caret frac gamma minus 1 gamma minus 1. T 2 equals t 1 p 2 p 1 gamma minus 1 gamma. Display style t underscore 2 equals t underscore 1 left frac p underscore 2 p underscore 1 right caret frac gamma minus 1 gamma. Topic: Graphing adiabats. An adiabat is a curve of constant entropy in a diagram. Some properties of adiabats on a PV diagram are indicated. These properties may be read from the classical behavior of ideal gases, except in the region where PV becomes small, low temperature, where quantum effects become important. Every adiabat asymptotically approaches both the v-axis and the p-axis, just like isotherms. Each adiabat intersects each isotherm exactly once. An adiabat looks similar to an isotherm, except that, during an expansion, an adiabat loses more pressure than an isotherm, so it has a steeper inclination, more vertical. If isotherms are concave towards the northeast direction 45 degrees, then adiabats are concave towards the east-northeast 31 degrees. If adiabats and isotherms are graphed at regular intervals of entropy and temperature, respectively, like altitude on a contour map, then as the eye moves towards the axes towards the southwest, it sees the density of isotherms stay constant, but it sees the density of adiabats grow. The exception is very near absolute zero, where the density of adiabats drops sharply and they become rare. See Nernst's theorem. The following diagram is a PV diagram with a superposition of adiabats and isotherms. The isotherms are the red curves and the adiabats are the black curves. The adiabats are isentropic. Volume is the horizontal axis and pressure is the vertical axis. Etymology. The term adiabatic is an anglicization of the Greek term adiabatos, impassable, used by Xenophon of rivers. It is used in the thermodynamic sense by Rankine 1866, and adopted by Maxwell in 1871, explicitly attributing the term to Rankine. The etymological origin corresponds here to an impossibility of transfer of energy as heat and of transfer of matter across the wall. The Greek word adiabatos is formed from privativa, not, and diabatos, passable, in turn deriving from dia, through, and bainin, to walk, go, come. Topic: Conceptual significance in thermodynamic theory. The adiabatic process has been important for thermodynamics since its early days. It was important in the work of Joule, because it provided a way of nearly directly relating quantities of heat and work. For a thermodynamic system that is enclosed by walls that do not allow mass transfer, energy can pass in and out only as heat or work. Thus a quantity of work can be related almost directly to an equivalent quantity of heat in a cycle of two limbs. The first is an isochoric adiabatic work process that adds to the system's internal energy. Then an isochoric and workless heat transfer returns the system to its original state. The first limb adds a definite amount of energy and the second removes it. Accordingly, Rankine measured quantity of heat in units of work, rather than as a calorimetric quantity. In 1854, Rankine used a quantity that he called the thermodynamic function, that later was called entropy, and at that time he wrote also of the curve of no transmission of heat, which he later called an adiabatic curve. Besides its two isothermal limbs, Carnot's cycle has two adiabatic limbs. For the foundations of thermodynamics, the conceptual importance of this was emphasized by Bryan, by Carathéodory, and by Born. The reason is that calorimetry presupposes a type of temperature as already defined before the statement of the first law of thermodynamics, such as one based on empirical scales. Such a presupposition involves making the distinction between empirical temperature and absolute temperature. Rather, the definition of absolute thermodynamic temperature is best left till the second law is available as a conceptual basis. In the 18th century, the law of conservation of energy was yet to be fully formulated or established, and the nature of heat was debated. One approach to these problems was to regard heat, measured by calorimetry, as a primary substance that is conserved in quantity. By the middle of the 19th century, it was recognized as a form of energy, and the law of conservation of energy was thereby also recognized. The view that eventually established itself, and is currently regarded as right, is that the law of conservation of energy is a primary axiom, and that heat is to be analyzed as consequential. In this light, heat cannot be a component of the total energy of a single body because it is not a state variable, but, rather, is a variable that describes a process of transfer between two bodies. The adiabatic process is important because it is a logical ingredient of this current view. Divergent usages of the word adiabatic. This present article is written from the viewpoint of macroscopic thermodynamics, and the word adiabatic is used in this article in the traditional way of thermodynamics, introduced by Rankine. It is pointed out in the present article that, for example, if a compression of a gas is rapid, then there is little time for heat transfer to occur, even when the gas is not adiabatically isolated by a definite wall. In this sense, a rapid compression of a gas is sometimes approximately or loosely said to be adiabatic, though often far from isentropic, even when the gas is not adiabatically isolated by a definite wall. Quantum mechanics and quantum statistical mechanics, however, use the word adiabatic in a very different sense, one that can at times seem almost opposite to the classical thermodynamic sense. In quantum theory, the word adiabatic can mean something perhaps near isentropic, or perhaps near quasi-static, but the usage of the word is very different between the two disciplines. On the one hand, in quantum theory, if a perturbative element of compressive work is done almost infinitely slowly, that is to say quasi-statically, it is said to have been done adiabatically. The idea is that the shapes of the eigenfunctions change slowly and continuously, so that no quantum jump is triggered, and the change is virtually reversible. While the occupation numbers are unchanged, nevertheless there is change in the energy levels of one-to-one corresponding, pre- and post-compression, eigenstates. Thus a perturbative element of work has been done without heat transfer and without introduction of random change within the system. For example, Max Born writes, "Actually, it is usually the adiabatic case with which we have to do, i.e. the limiting case where the external force or the reaction of the parts of the system on each other acts very slowly. In this case, to a very high approximation c 1 2 equals 1 c 2 2 equals 0 c 3 2 equals 0. Display style c underscore 1 caret 2 equals 1 c underscore 2 caret 2 equals 0 c underscore 3 caret 2 equals 0. That is, there is no probability for a transition, and the system is in the initial state after cessation of the perturbation. Such a slow perturbation is therefore reversible, as it is classically. On the other hand, in quantum theory, if a perturbative element of compressive work is done rapidly, it randomly changes the occupation numbers of the eigenstates, as well as changing their shapes. In that theory, such a rapid change is said not to be adiabatic, and the contrary word diabatic is applied to it. One might guess that perhaps Clausius, if he were confronted with this, in the now obsolete language he used in his day, would have said that internal work was done and that heat was generated though not transferred. In classical thermodynamics, such a rapid change would still be called adiabatic because the system is adiabatically isolated, and there is no transfer of energy as heat. The strong irreversibility of the change, due to viscosity or other entropy production, does not impinge on this classical usage. Thus for a mass of gas, in macroscopic thermodynamics, words are so used that a compression is sometimes loosely or approximately said to be adiabatic if it is rapid enough to avoid heat transfer, even if the system is not adiabatically isolated. But in quantum statistical theory, a compression is not called adiabatic if it is rapid, even if the system is adiabatically isolated in the classical thermodynamic sense of the term. The words are used differently in the two disciplines, as stated just above. See also: adiabatic conductivity, cyclic process, first law of thermodynamics, heat burst, isobaric process, isenthalpic process, isentropic process, isochoric process, isothermal process, polytropic process, entropy, classical thermodynamics, quasi-static process, total air temperature, magnetic refrigeration.